in our general club today. Today we're going to talk about optimal transports for generating some transition states. It's from chemistry that I don't know. Anyway, we are focusing on generating something using optimal transport. So let's begin by reading the abstract together. Are you done? So, did you find any gap sentence? So yeah, there is a gap sentence, meaning that the current algorithms of generating transition state is not easy. So they developed some machine learning based methods, namely the React optimal transport. So some keywords are colored in blue or purple or green. So there are two states, reactants and the products. This is the before and after. Then in the intermediate state, there is something called transition state, which is difficult to generate. That's the purpose of this method. However, our general club will be focused on the method rather than the chemical effects. So we will focus on the two things. First one is the basic introduction to optimal transports. The second one is what is called the flow matching, which is a method generative model. So let me first present you an overview of what's going on. So as I told you just before, transition state is an intermediate state before reactants and products. So if you recall some chemistry, two things, methane and oxygens, become CO2 and water. So the before one is called reactant, and the after one is the product. However, in the intermediate stage, there is some stage called transition state. Why it is important? So if you draw a picture of energy, then you can see that from the reactant, in between the reactant and the product, suddenly there is an increase of energy. And this is where the transition state is located. And why it is important? There are two reasons. Actually, transition state tells us how fast a reaction is happening. So, okay, this is not important to our lecture, so I will just quickly mention it. So, if we measure this energy gap, which is the energy of transition state and the energy of reactant, we can know the speed of reactant. Is it right? Maybe. So we use these facts to design some catalysis. Catalysis is some artificial material to make reaction faster. So in order to design a catalysis, we strongly use the transition state. So the lesson is that generating transition state is so how do we generate? We will use the generative AI. So what is generative AI? Generative AI is a type of neural network. What is neural network? Neural network is basically a function of an input and output. Neural network. If we train this given data, so there are input and output pairs, 3 pairs, we train it to the machine. Then we obtain a function, so approximate function that the machine trained. And after that, we will test a new input 3, and then this function will give us maybe 6 or something similar to 6. Okay, this is neural network. What is generative neural network? So let's say we have a picture of a dog, and we want to change it to the Ghibli style. So that we want to finally obtain this picture. Here we mean that we put some photo and generate some other photo. So this is what's going on with the generative AI. However, how can we do this? Is the problem. How can we generate a picture from other picture? So we have 2 pictures. We first transform the pictures to some mathematical material, namely numbers or matrices or vectors. Then we put many real photos of dog as an input to the neural network. And as an output, we have many photos of each corresponding Ghibli style. Then we again put it in the machine. Then it is a bit maybe jump, but there is a distribution or characteristics of the original photo of real dogs. So what we want to do is to run the map from these original photos to the Ghibli style photos. Having known this, if we put another new input, which is a sample from this distribution or characteristics, then from this map we obtain the Ghibli style. This is the basic fundamentals of generative AI. So we will use this to generate a transition state. This is a bit complicated photo. So in the previous slide, I run the map from one distribution to another. Here, in order to generate a transition state, we run a distribution from initial state to the target state. So that if we start with some arbitrary point sampled from this initial distribution, then it follows to the neural network to obtain some target distribution. So I wrote here the diffusion model. This is not our central focus, but it is one of the most important generative AI. It uses some noisy, SD, stochastic equation. So again, diffusion model. So diffusion model, as I just mentioned, it uses some stochastic equation, which means that we put some noises during the training. So as an output, if we begin with some sampling, it achieves some output, but it is noisy. So every time we try, we obtain some different results. So this might not be very useful. So the authors try to think some deterministic way to generate something. This is one purpose. So here, the middle picture in the right-hand side, here on the right side, is the transition state. So we basically run a map from left to right. So as a new input here, we obtain the transition state. This is the basic philosophy of this paper. In order to do this, we should learn some deterministic inference here, and this comes from optimal transport. So naturally, we have to learn some optimal transport. Let's study some basic of optimal transport. So optimal transport, as its name suggests, is to move something in an optimal way. So let's begin with some basic problems. So our friend will move to Incheon soon. So here are the luggage of his luggage in IBS. He wants to move this luggage to Inha University in this configuration. So his desired design is fixed. So it remains to set some function t of how to move these luggages from here IBS to Inha University. In a mathematical language, this will be a function from x1 to x5 to y1 to y5. Okay, so what is t of x3? T of x3 is y3, you can check. And t of x2 is y5. So I deliberately distinguish the color of same luggages to distinguish that, to emphasize that there are various choices of map t. For instance, we can have like this: t of x2 is y5. But if the colors are slightly changes, we can set a different function. I mean, the configurations are the same, but the function is slightly different. Here, t of x2 is y4. So, in order to transport in an optimal way, we have to first consider the map t. However, this is not the end. So let's formulate this problem in a more mathematical way. So let's think about the real line, and there are 5 numbers each as an input. I mean, luggage in IBS and luggage in Inha University. x1 to x5 and y1 to y5. From the map t, they are moved like this, for example. However, we can actually write the whole thing in one real line instead of 2. For instance, if we depict only 3 points in the domain, x1 to x3, they are moved like this. So x1 will be moved to y5, and x2 will be moved to y1, and x3 will be moved to y2. As you can see, so what should we consider from this transport? So if we move some luggage longer, then it will be more costly. Or if the luggage is heavier, then it will be more costly. So first, the distance should be considered, namely the distance between y5, the target point, and x1. Or in other words, t of x1 minus x1 should be important in a similar way like this. So in the previous slide, the choice of map was important, and now how long and how heavy the luggage should be transported is important. How long means that the distance between t of x and x, and how heavy means the initial distribution, initial weight of luggage. Actually, you can think of it like a probability distribution by simply normalizing it. So, the French mathematician Monge formulated this problem as follows. So, optimal transport means to minimize the whole cost, how long multiplied by how heavy the luggage is. And we sum up of this cost with respect to the whole domain. And in terms of the probability density, this can be formulated as follows. So from this initial distribution mu and the target distribution mu, we have a map T, and we have to choose an optimal T in such a way that the cost function is minimized as follows. So in the previous example, I gave you some discrete distribution, but in generally, if you consider some continuous distribution, continuous probability distribution, you can write it like this. Actually, I wrote it by square, T of x minus x squared, but actually this can be any distance in the space that you are considering. And actually the choice of distance is very important of the property of optimal. And here mu of x means the initial weight or initial distribution. What is this T sharp mu? T sharp mu, I will explain this terminology. T sharp mu is called the push forward measure. So by this map T, mu is moved to the space of the target. And here this formula T sharp mu equals to nu means that the measure mu, the probability distribution mu will be moved to T so that it will be equal to nu. Mathematical definition. Push forward measure. Actually, what Monge problem has a serious problem. Let's say we have a following distribution. This is our initial distribution, and this is the final distribution. Can we make a map from orange one to the sky blue? Can we make it? No, because the domain has 5 elements and here has 6 elements. We cannot go from 5 to 6. Match the function. So, I mean the Monge problem is very restricted problem. So, yeah, there is some problem. In order to overcome this, so this is the Monge problem. Russian mathematician Kantorovich generalized this into the following setting. So if you look at the Monge problem again, it is a bit dynamical, meaning that we have a cause and effect. So we move from orange to sky blue. It is the intuitive meaning of transport. But Kantorovich tried to treat them as equal. So instead of moving from one to the other, so you think of some joint distribution, gamma x. Maybe everybody is, so I will tell you the joint distribution. So joint distribution means that if you put some specific number x and y, it gives some probability of that x and that y. Here the restriction of gamma, x and y is that its marginal to x should be mu and its marginal in y should be mu. This is the restriction. And such restricted joint distribution is called the plot plane between mu and mu. Finally, Kantorovich generalized Monge problem as follows. We should find a coupling between mu and nu such that it minimizes the cost of this double integral. Here again, the x minus y squared is just my choice of the distance, Euclidean distance. And I will not tell you this deeply, but if you compare Monge problem and Kantorovich problem, you can notice that Kantorovich problem, so it is a function of gamma, right? We have to choose gamma. And this function is actually linear in gamma. However, Monge problem, the choice of t is not linear in t. So that's why Kantorovich problem is easier to solve. Questions? Okay. So we run some basic optimal transports. Now we will move to generative AI, which is called flow match. So I have to tell you something more about optimal transport. Optimal transport is most advantage is that it gives us a distance between measures. So let's begin with distance between 2 points in a plane. 2 points of distance, 2 points have a distance like this. You can simply draw a straight line. However, if you think about the very abstract probabilities distributions in the space of probability, this is hard to imagine. This is infinite dimension. How can we say the distance between mu and mu? So there are various notions of how similar the mu and mu is, such as the divergences, Kullback-Leibler divergence, something like this. But that divergence is not a metric. It's not a distance. True meaning. Here, using the optimal transport, we can define a distance between two measures, which is called the Wasserstein distance. So it is, as you can see the formula, this is exactly the cost between a transport from mu to mu, where the gamma is chosen to be the optimal transport thing. So I didn't tell you. If the cost is minimized by gamma, then the coupling gamma is called the optimal transport plan, or the optimal coupling, or optimal transference plan. You can guess the reason why here there is 2. It comes from the reason of the choice of the distance. In general, we have Wasserstein p distance. You can put arbitrary p here. Then we can define some straight line. The shortest distance from one measure to another. What is straight line? If we have a plane and if we have 2 points x and y, then the shortest distance from x to y is a straight line simply. And actually this can be parameterized using t. Okay? So 1 minus t and t means that you divide take some internal points here between x and y. In a different geometry, in a sphere, you can also think the shortest distance. If you imagine you are taking an airplane, you are on the spherical domain, so you should move almost like a straight line, like this. Such straight line is called geodesic, shortest distance. But what about a straight line between 2 measures? How can we compute this? What is a geodesic in probability space? You can directly imagine this in a similar way like the Euclidean way. However, this is not really true. So far I presented you 2 formulations of optimal transport, Monge problem and Kantorovich problem. There is another formulation that I will now just present. It's called by Benamou-Grenier formulation. It is invented by 2 mathematicians, Benamou and Grenier. So we have a Wasserstein distance. here the reason that I put infimum is that I can think about the general gamma. So the Wasserstein distance, square of Wasserstein 2 distance is the minimum of this following host with respect to the varying various gamma, the joint distribution. Actually, if you recall the Kantorovich formulation picture, it is not dynamic, it is static. So I want to make some dynamic formulation because it gives us the true meaning of how one measure transforms to the other. Therefore, Benamou and Grenier formulated, which is what is called the dynamic optimal transport, as follows. A bit complicated looking, but it is basically, you can think of U as a velocity, and rho is the probability. So this means like the sum of the square of velocity. So this is something like kinetic energy. Here, initial distribution, initial rho 0 is the initial distribution U, and the target point, the boundary point is the target distribution. Here, rho t satisfies following equation, which is called the continuity equation. Maybe you heard this from Professor Eugene Cho's lecture or in other places. So the Wasserstein distance or the optimal transport problem can be formulated using a flow. This is a flow of measure. So it means that from this initial measure, it flows with the velocity u to become a target point. So boundary conditions rho 0 and rho 1 are fixed, and we have to choose some appropriate velocity. In order to, I mean, you don't have to think about this deeply, but let me tell you some context of this equation. This comes from fluid dynamics. So like this, if you imagine an air or some water, it can be described by some mathematical equations, which is called the Navier-Stokes. So Navier-Stokes consists of many things, but essentially there are two things. First, if you think about the move of air, then air must have some mass or a density, rho. And the density flows along this equation, continuity equation. Actually, the fluid also have not only have a mass, but it also have a velocity or momentum. So momentum equation is written like this. This is the Navier-Stokes equation people are most considering. Anyway, this continuity equation and Benamou-Grenier formulation comes from the description of fluid dynamics. Actually, it is compressible fluid dynamics. So fluid can be divided to compressible and incompressible. Incompressible, if you imagine a water, if you put some water here, if you put it, push it, it cannot be compressed. But if this is an air, then you can compress. That's why compressible and incompressible. So now, having known this, we can define a geodesic between mu and nu. So mu and nu are measures on real line, and gamma is the optimal transport plan. Wait, there is my. So we can consider a map from R2 to R, which gives us some interpolation. So given x and y, we get this. So this is motivated from the geodesic inner plane. Then let's record the push forward measure from one space to another. You move a measure from probability density from one to the other. Then you can define a push forward, so we have two spaces, R2 and R. We move a measure from R2 to R. And R2, the measure is chosen by the coupling, optimal coupling. And if you move the optimal coupling gamma to R, you obtain a measure in R. R is where mu and nu are living in. So what I want to say is that this push forward is the geodesic between mu and nu. I mean the shortest distance of transporting one measure to another, one probability density to another. So in a picture, you start with mu and you finally want to become nu. And we want to know the intermediate step. Actually, this can be anything, but if you want to do it in an optimal way, you have to choose this. But if you record the Benhamou-Grenier formulations, there is a flow, velocity vector, ut of x, coming from mu to nu. So from this flow, if you sample a point from the initial distribution and the target distribution, this initial point will move along this fluid to reach x1. Then what is the intermediate step, xt? Actually, the xt is computed, given by this following fluid vector, vector field, so ut of xt. The trajectory of xt is given by this fluid, which is simply just a straight line connecting x1 and x2. So what I want to say is that we will use this vector field to our flow matching thing. So let's go into the flow matching. So what we want, if you record the picture transforming a original dot to the Ghibli picture, we have a distribution of original dot picture mu. One thing to say is that distribution is same meaning with measure, same meaning with density, and same meaning with load. But in practice, we don't know the distribution or characteristics of target distribution we want to obtain. We don't know the full information. We just know some samples that we obtain from the target distribution. So it means that we only have some pairs of input and output. In order to generate something in this situation, we first think about transforming the initial distribution mu to nu, only one point. Instead of thinking the whole distribution, we just think one point distribution, which is Dirac delta. Then from the flow that I just said you in the previous slide, the vector field from x in mu to g is given by the following difference of final point and initial point. Actually, doing something, transforming mu to here, there are various ways of doing this. If you see this picture, initial distribution is depicted by blue, and the target point is red. Okay. But if you see the trajectories, these are not straight line, so which means that it can be various ways. But if you want to do some optimal transport, you should connect it using the straight line. So we are almost done. So I will just briefly tell you the overview of flow matching. So our goal is to transform initial distribution to target distribution. I just told you continuously. First, we sample many points from the target distribution. then we take some conditional probability paths. I mean, this conditional probability path. Instead of thinking the whole distribution, we take some conditional probability paths like this. Then having known this, we run some neural network which satisfies and minimizes its cost to run these trajectories. But one can wonder the following. So what's the meaning of this? I mean, we have to run the whole distribution. Why do you do such thing? Why do you do this with only one point? This can be a wonder. But it turns out that look at this loss function, LFN. This is the original cost function. You have to run the neural network, catch the true vector field. Whereas the LCFM, conditional flow matching, is to run some conditional flow. But it turns out that optimizing LCFM is equal to LFM because their gradients are the same. So if you perform the gradient descent, you can obtain some same optimization procedure. So this is the strong meaning of flow matching. You can do this with conditional vector. So this is what we do with samples. This is what we do with full inference. Having done this with samples, you can start with these glue points to obtain final target. Okay. This is flow matching. And here the authors choose the optimal vector field that I just continuously presented by connecting the final point and initial point. Okay, as an application, let's go back to transition state. We have a reactant before, the material before, we want to, then it moves to the material after, which is products. And in the intermediate stage, there is something called transition state. And the authors did the following. So they learned a map from the data. They learned the data pair of reactants, input and output. And they put as an input, which is a mean value of this reactant and product. So you put this left hand side mean value. Then from this map, it gives us the transition state from the flow. Okay. To sum up, we put as an input mean value. As an output, we obtain a transition state. And actually here, the functional flow matching, conditional flow matching is given by this vector field. Yeah, this is the summary. Actually, there is one thing that I didn't tell you. As you can see, the molecules have some geometric structures. So they have lots of symmetries, like rotational symmetry or translational symmetry. You can impose the symmetry to your neural network. If you are curious, you can look at these two papers, or I can present it later. And one other thing is that the authors actually did the same process before with the diffusion model. So if you compare the flow matching method with the diffusion model for the same task, you can look at this another Nature paper. But they argue that their optimal transport method is better than their previous diffusion model method. Thank you.